Yes.
Hello.
Hi, Sophie. Welcome.
Many thanks.
Is it? Are we recording, Vahan?
Yes, it's all recording now. All going to be on YouTube.
Okay, cool. All right. Thanks, Vahan. So yeah, hey everyone. I'm excited to present this paper on anomaly detection in multiplex dynamic networks. So this is kind of building on a lot of the work that's happening in like graph learning, but specifically, I guess the sort of journey that graph learning's been on has been on like starting with static graphs. So this is just like one graph, one network. Then I guess the next phase is like, okay, how do you consider dynamic networks? So this is networks that change over time. In fact, a lot of graphs and networks in real life are dynamic networks. If you consider like transactions, or if you consider well, yeah, like cryptocurrencies or shopping on Amazon, these are things that like networks that change over time. So you might have like edges that are only present for a certain periods of time and then disappear and then maybe reappear later. So then this is kind of the study of dynamic networks. And then this paper focuses on multiplex dynamic networks. So what that means is we're dealing with dynamic networks, but with different types of edges. So that's what multiplex means. And we'll get into like, how that's structured or how that's presented. So yeah, I guess the interesting thing in this paper really is the multiplex part. So a lot of like approaches for studying networks, as it says here, focus on like one type of connection between vertices. But actually in reality, in real networks, there might be different types of edges which yield to multiplex networks. So they proposed this kind of new framework called Anomaly, which is an unsupervised edge anomaly detection framework. And it has some pretty cool like things that they introduce, and they build off some previous papers. So I'll go into a little bit like what those are. Cool. So I guess the main thing they're trying to solve is how do we detect anomalous edges in real world networks? And what they claim is that to really be able to detect anomalies, you need to pay attention to, first of all, their dynamic nature. So you need to consider the networks are dynamic. You lose a lot of information if you think that if you treat them as static graphs or static networks. But I guess the biggest contribution from this paper is like, you also gain a lot of rich information if you consider different kinds of interactions between vertices, so different edges. So they give some examples like interactions between people can be like social or professional. So for example, they use later on the citation network, and they consider not just citations, but citations on different topics. So these are like different types of edges. So you might cite a paper on the topic of data mining, or you might cite them on like biology or something like that. So yeah, it says existing approaches to anomaly detection suffer from a couple of different things. So one is that a lot of existing methods use kind of like handcrafted features. So looking at different network properties, looking at local, like highly dense clusters as a way of identifying anomalies. And so these are usually very fine-tuned to like a particular application and don't generalize to different domains. So you might have some features that work really well in one type of network, but might not generalize to another type of network. And then the second thing is that they treat kind of all connections the same. So effectively, yeah, again, like we said, you might have different types of interactions. And usually in the study of like multiplex networks, they consider like each interaction like each type of relation equally important. But what they do in this paper is they come up with a method for learning the importance of different layers in the task of anomaly detection. And then the third thing is that this paper focuses on specifically on edge anomaly detection, whereas a lot of previous papers focus on node anomaly detection rather than edges. So it's like another kind of different take on detecting anomalies. So as I said, they build on some previous papers, and I really recommend, like, if you're interested in this paper, there's a paper called Roland, which is kind of what the contribution for the Roland paper was taking GNN methods applied to static networks and basically repurposing them to work on dynamic networks. And the way they do that is they consider this idea of hierarchical node states, where you have at each time step in the dynamic graph, you consider the state of the node in the previous time step, and you kind of treat it a bit like a RNN, where you consider like the sequence of node states. And then the other, so that's like kind of one idea that they take from another paper, and then they also use this concept of like selective negative sampling to learn edges in an unsupervised manner. And so I'll get more into that, like how that works later. But some of the, I guess, like, it's really cool. What I find cool is like some of the applications for this, particularly this brain network. So typically how they describe like brain network are analyzed in the past is as like a single layered like network, so not multiplex. So let's say you have like 40 people where you have like MRI scans. They might, what they would do is they would sort of average all of the brain networks and then study that network. However, that, you know, in averaging everyone's brain network, you lose a lot of information. So when you, what they do in this paper is they treat each individual's brain network as a separate type of relation. So let's say the nodes represent different parts of your brain, and then the edges have a property, which is which person do they belong to. And in doing so, they can like capture, or they can detect anomalous edges like better. And also they can start to make like inferences about where, like, for which people have like the most anomalous connections, and like in what parts of the brain. They have some really cool results at the end of the paper. And they specifically look at like people with ADHD and how the brain connections differ to like neurotypical people. And the second one is like fraud detection in blockchain networks. I'm a bit less interested personally in that application, but you know, if that's your thing, then also there's like what it considers here is like, rather than looking at a single blockchain, can you consider fraud detection across multiple blockchains? And it gives you sort of a more rich perspective of like what's happening in the network, rather than just looking at one blockchain, and you might be able to capture criminal activity much like earlier and better. By the way, as I'm going, feel free to jump in if you have questions or comments. Yeah, I think it's good to like have more of a discussion about these things if you have something you want to say.
One thing I've been wondering to myself is, what's the difference between treating different edge types as just a feature of an edge and treating them as like separate edges? You know, or is it the same thing? Do they what are they doing?
The way I interpret it is, and well, I guess we'll get more into it, but they treat each so each different edge type they treat as like its own graph. So that's why they have this idea of like layers, and so each layer treats a different considers a different edge like type, and learns different node embeddings So almost like you have different node embeddings based on the type of like link that you're considering. And I think maybe that's the difference rather than just learning like one node embedding per node, if that makes sense.
But that's
So you
not
have, like-
super scalable to say like having 1,000 edge types, right?
Yeah, that's actually something they don't address in the paper, and it's probably something that I was like keen to understand. The maximum, so in all the data sets they look at, the most edge types there are is 10. That's like the highest.
Why would you have 1,000 edge types?
Like in knowledge graphs, you would, because there's many different types of relations between entities.
Yeah.
But yeah, it probably there's a lot of real world. So Vahan's right next to me, just so you know.
Yeah.
But there's a lot of real world applications where there's probably a limited number.
Yeah.
I was just thinking that there's also there's GNNs, which, and maybe this is one of their baselines, but like there's GNNs that take into account edge features, and I could see that being just another way to do the same thing.
Yeah. I think they have some here. They have like other methods that they present here in terms of like multiplex graph learning. Yeah, I think then they then compare them in the experiments. I'm going to skip over this like related work, but I think if you're interested in dynamic graphs, I would say like check out this paper because
Good evening. Thank you for
Sorry?
taking the call. I know it's a little bit late in your day.
Sorry, Ashwin, was that a question? Yeah. Can you hear us, Ashwin?
Hello.
Hello, is it just me? Guys, is it just me that can't fit?
No. Oh, I can't hear. I couldn't hear him either.
हाँ, connection रुक के आ रहा थोड़ा बस. Got it.
Ashwin, I'm going to mute you. That's okay. Okay, everyone can still hear me though, right? Okay, cool, good. All right, yeah. So check out Roland if you're interested in like graph learning on dynamic graphs. And it kind of, I quickly skimmed it, and it looks like this paper is basically a copy pasting of that, but then applying to like multiplex. So yeah, it really builds on that one. Cool. So let's get to the fun part. Cool. So let's look at what's happening. So this is effectively so on the right, this is like what Anomaly looks like. So you have the contributions are like this, the snapshot encoder, which I'll go into now, and then they have like this kind of scoring function, which basically scores the edges based on the probability of them being anomalous, and then they use a margin loss, which also uses negative sampling as a way of doing this kind of unsupervised anomalous detection. But the cool thing is this snapshot encoder. So what's happening? So you have each color is a different relation type or a different layer, as they call it. So in the case of the brain network, you might have the same nodes, but for one person, some of the edges will be present. For others, like those edges might not be present. And so what happens is each one of these layers is put through a GNN layer. And then this is really the part that Roland introduces, which is you have this embedding update step. And what that does is it combines the current node embedding at this snapshot with the node embedding at the previous time step. So this is where you incorporate the information from the previous snapshot of the network. And then the thing that this paper introduces is this attention layer. So it attends over the different relation types or the different edge types or the different layers. They use a lot of different terminology. I'm going to call them layers from now on. So it attends over the different layers. And so in doing so, it learns the importance of different layers on like I guess the layer that you're like predicting on in terms of like trying to find the probability. The reason they do that is so that rather than considering that each relation type is equally important when you come to calculating the probability of an anomalous edge, they do this attention to basically learn weight the importance of different layers on other layers, if that makes sense.
One quick question. So the different relations, when they call them layers, they are not, they're not some network layers either, right? So
No, they're they're sort of like layers in a different dimension.
yeah. That must have confused me and when reading the paper.
Yeah, because they use layer sort of interchangeably. So you have like what I think is, so for each relation type, for each relation you have a different sort of network, or I guess like weights that you're learning. And then you have like the attention layers so that they each attend on each other and then
I think
keeps
it's
going.
only the GNN itself that could have in principle multiple steps, right? Multiple aggregation steps, which you could consider a layer of some sort.
Yeah.
Okay. Thank you.
Yeah, exactly. So I guess to go into a little bit more what it does. So you have like for each layer you do I guess I'm not as familiar with GNNs, but you do what I assume is like quite a typical GNN step where you do like message passing within that layer, within that relation type. So you create those like embeddings for the nodes. You then pass in the like node embeddings at the previous time step, and you do like they use a gated recurrent unit here to to combine the information from the current the current embeddings with the embeddings at the previous time step. And this is what they so they call this the layer aware embedding matrix. It's basically just the embedding matrix at that for that particular relation type for the nodes. That's kind of all it is.
Can I ask a question?
then,
Yes, sorry. This
yeah.
became a bit confusing. I thought the attention layer was between the time steps, which represent the graph layers. Or is it the multi-graph that also changes over time?
It's a multi-graph that changes over time.
Oh, so you have the multi-graphs graph layers, you have the time steps, and then you also have the GNN layers.
Yeah.
Okay, that makes that's better. And then the time step is down with the GRU.
Yes, exactly.
Which makes more sense. Because I thought they would do the attention layer for the time steps also. But okay.
No, yeah. So they do. So you do the GNN layer. So for each relation type, you apply the GNN layer. You combine it with the previous time step using a GRU, and then they attend over each other to create what they call this like network level embedding. So this network level embedding is one time step considering the whole network, all types of relations. And so this is like where they learn the attention weights.
Can I go back to the application? So because again, I thought the multi-graph is a multi-graph because of the time steps. So what do the multiple layers in the graph represent?
Different edge types.
And you can't put different edge types on as edge features.
Well, that's what Peter was asking, right?
Right.
It's I don't personally know. Yeah, my interpretation is that you're effectively treating each. So for each edge type, you're sort of creating a separate network, and you're learning different weights. So let's do an example. So let's say we have like the citation network, which is one of their examples. So they have a citation network, and the red might be citations for graph learning. Another one might be for data mining. Another one might be for biochemistry. So you have like different edge types depending on the topic. I guess what they're saying is that learning what contributes to an anomalous edge in data mining might not be exactly the same as the features that predict an anomalous edge in biology. And so maybe that's why they have they separate them, almost like learning them differently, but all in one framework that they can learn end to end.
Okay, makes sense.
It might also be that there's somewhat the implicit assumption that whatever happens within one layer is more important in the first step than what happens in between layers, which is why the GNN sort of looks first at what happens inside the layer, right? And then only afterwards it's sort of compared by the attention. So that might make some sort of prior assumption about what's what. You would think that the different edge features could simulate that if the GNN has some sort of filtering or learned filtering in between features, right?
Yeah, because I guess so previous methods, I think, would basically do like this, and they just do it. They'll just do it like once. So that's like what they call not a static network, but like a simple network, where they only have you have one edge type. But here they do that like repeatedly over different edge types.
One thing that I was sort of wondering, they didn't talk really much about any neighbor properties of what's the A matrix called in these graph neural networks, right? So do we treat in this problem as if every vertex is sort of a neighbor to every other vertex, and only via the edge properties itself do we get neighborhood, and just say that edges could be zero, and then this essentially cuts off the information flow between them? Or
no, I think so the network already defines like what are the edges. So you have the vertices and you have a set of edges, and then this network is supposed to, it computes the probability of each edge being anomalous.
Yeah, it's just a bit confused how this would work in practice. Say we have a transaction network.
Yeah.
Would an edge be whenever there ever was a transaction between two players that we would consider a edge, and if there never was an edge, we always would consider it zero? Or
so you consider it at different time steps. So when it comes to predicting, so for each edge within like a particular time step. So here our goal is to detect anomalous edges in edge T. So basically at that snapshot of the network, you have the network looks a certain way and you have certain edges, and you predict which ones are anomalous.
So it's not just the features that are that dynamic, it's the edge itself that All right, that makes sense. Thank you.
Yeah, it's the edge itself. Yeah. Cool. Yeah, so we have this attention mechanism, which creates this network level embedding, and then that all gets combined to create the layer aware node embedding for each for each layer at each time step. So that's like effectively what's described in this snapshot encoder. So really, I guess the main things is like you pass in, you have a separate GNNs for the different edge types. It gets the embeddings get updated based on the node embeddings at the previous time step, and then all the layers attend on each other, basically. So that's what generates ultimately the, so then you have, that gives you these, which is the layer aware node embeddings for each relation type, in this case, red, blue, green. And these get passed to the scoring function. So what is the scoring function? Oops, sorry. The scoring function, what it does is it takes, so for an edge between nodes U and nodes V, it basically uses the learned embeddings for U and the learned embeddings for V, and it takes the norm, and basically there's a couple of like where you have an activation function, and then there's these two hyperparameters. They don't really mention much, at least that I saw, about these hyperparameters and how they control it. I think they might do in the experiment. But this is, so what I thought, because they kind of make a big deal about detecting anomalous edges, but I suppose all the previous work can probably be extended by using this like this way of computing the probability for each node. Yeah, and then the last thing is they use a negative sampling approach to create like anomalous connections. So they talk a little bit about, they talk more about this in the appendix. Effectively, the way they train is they corrupt the network, and then they basically train by sampling like those corrupt edges versus like edges that exist in the network. And I think that's how they that's how they train the network.
Yeah, that was another part that I was thinking about, because like the whole idea, how do they guarantee that there's no anomalous edges in the graph anyway? You know,
Yeah.
and because when they get a new graph at inference time, that graph isn't gonna, if it has anomalous edges in it, like right now, anomalous edges in historical graphs or in their data set are treated as like positive edges, as edges that should be there.
Yeah.
And by corrupting it, they're saying they're negative. And then at test time, they want to, or at inference time, they're going to want to choose. They're going to want to find those same edges. So how does that work? Like, did they curate the data set so it doesn't have like weird edges in it, or maybe they?
Yeah. It's a good question. I don't know. I feel like what they do, they sort of make the assumption that there's a very small amount of anomalous edges, so it doesn't matter. But if I go to the appendix, they have they go into a little bit more detail about like how they create the data set. So yeah, so as I said, they inject anomalous edges. They sort of extend this injection of anomalous edges into the case of like multiplex networks. So this is like another thing that they do differently. So the way they add edges depends on, they effectively only they only inject an edge where two nodes don't have an edge in any of the layers. Because what they say is that if there's a yeah, if they have an edge already in one of the layers, then it's likely they'll have it in the other ones, and so that's not like what they want to learn. So yeah, they have this kind of they do like 50-50 in terms of single networks and multiplex. But yeah, it's a good one.
Does it mean that anomaly is highly correlated with there being one edge only in one graph layer?
That's what they say, yeah. So it says
that means the whole learning maybe just reduced to that, right? Maybe that's all you need to learn to find anomalies.
yeah. But it seems to work in practice in terms of the training. I guess that's why they do this, like half of the edges they inject, they use this method, and the other half they use like they inject in one of the single layers.
Okay.
Cool. So so what are the results? So what I think a cool thing is that they use 9 real world data sets. And they provide a lot of results for each. So they mentioned that I don't know what these data sets are, but so they compare performance in static and dynamic networks, as well as simple networks versus multiplex networks. And then they do an ablation study. So they have like lots of different ways of evaluating this. So so they have in this one, all of these are multiplex networks, so they all have multiple edges, multiple edge types. And so what they show is that the performance of like considering multiplex, of considering the fact that it's a multiplex network, improves the performance a lot. I will say though that for these two, it seems that they get pretty similar performance to this one. And I think that's because add graph is also an end-to-end approach, whereas the other ones are like handcrafted features. And so I think it probably shows that the effectiveness of using like an end-to-end learning approach versus versus handcrafted features, because these two baseline methods, what they do is they only provide network embeddings, and then they apply k-means clustering to get the node embeddings for the anomaly detection. So they basically work kind of similarly, or in some cases not, in some cases a bit worse than just considering it as like a single layer. Another thing that I thought was interesting that I've highlighted here in the improvements is that, so these three networks saw the highest improvement. And when I was looking at the table, I noticed that those 3 are the ones with like the most types of edges. It's a correlation, not a causation, but I thought that might explain like why they saw the greatest performance in those, because maybe there's more rich information captured by treating it as like a multiplex network. But yeah, on average, they saw like an 8% improvement in the anomaly detection compared to other methods. And it applies also to simple networks. So networks which only have one edge type, they similarly also see like an improvement, but it's only like a 2% improvement over add graph. And I think what they claim is that the reason this is because of the because they incorporate like the outputs at each time step using the GRU. So that's why they get slightly better performance. So because they consider the dynamic nature of the network. And then the last thing they do is this ablation study where they say, okay, what would happen is if instead of using a GRU, we'd use like an MLP instead. And then what happens if rather than using an attention layer, so rather than attending over the different relations, we like exclude it, or we do like a summation. So what the summation is basically like instead of having weights learned at the attention layer, they just add all of the relation types and aggregate it that way. And yeah, all result in slightly worse performance. I thought it was kind of interesting that that summation does better than like no attention or like nothing at all. I think it's probably because like there's information being learned at each layer that's useful for the other layers. And by layer, I mean different relation types here. So yeah, then they kind of consider, so these are like how you'd evaluate basically for anomaly detection, but then they say, okay, like what are the practical like use cases of this type of method? And so they consider two experiments. So one is detecting anomalous like events in the Ethereum network. So what they do is like at each timestamp of the graph of the network, they calculate the average anomaly score for the top 15 most like anomalous edges. And they find that the top, like some of the top points basically like relate to different events, like kind of major events that that lead to like lots of fluctuations in like the trading of cryptocurrency or Ethereum in this case. But also in the brain networks, I thought this was like super interesting. So they look at, they study, their data set covers 40 individuals, 20 of which have ADHD and 20 of which are in the control group. And here they consider, as I mentioned before, each layer, so each relation type is one individual. And so what they find actually is that 74% of all detected anomalies are edges in the brain networks of people in the ADHD group. So the anomalous edges are typically found with people who have ADHD. And then on top of that, of the people in the ADHD group, 69% of all the found anomalies are in the frontal and occipital cortex of the brain. So they can then like infer that there's something interesting happening in or unexpected happening in those regions of the brain which relate to having ADHD. And so they're able to, I guess in the past, or how they describe previous methods would have like averaged the brain network of everyone and studied that. But in doing this, they can see like the patterns in like different parts of the brain and find that most of the anomalies are detected in the people with ADHD. Oh, I think the last bit. So
last question before that.
Yeah.
I was just thinking, does it mean that the network learns attention weights that may represent correlation, accurately represent correlations between graph layers, right? Because if you're putting all 40 individuals as multiplex layers of the graph, then the attention has to be important there, right? To be able to classify ADHD. Did they at all look at how attention represents the the groups.
No, I don't think they looked into that. But yeah, it's a good point, right? Because the attention would probably tell you something about what it's learning from. Yeah.
Okay.
This is like just another visualization of the brain networks. Then so they have their code. Although I went on the repo and there's no code there, so that's not great. And there's one issue on the GitHub repo which says, "Where is the code?" And I just commented saying that was in November last year. so sadly, no code. Unfortunately, it's just an empty repository. It's actually quite sad. I feel like this should be picked up in the peer review and be like, hey, you didn't publish any code. Like, what the hell? You shouldn't have the paper published in Europe's if you're lying.
So they do, yeah. Yeah, I think it's hard because you might even want to go a step further and have like some kind of peer review of the code, but
yeah,
that's not possible to do double blind easily, I guess, and also it just would take way too much time.
That's almost a reproducibility study, which is useful, but of course the code might have been there and then been deleted. So you want to catch that situation too.
Yeah, I don't think that's the case. I think they just have they literally just created a test.py, which is an empty file. It's actually hilarious. I don't know how they got away with it. Cool. That's the paper. Does anyone have any thoughts or reflections or comments, questions?
It'd be fun to download the code and try it.
Yeah. Absolutely.
I had a more random question about, so I haven't really read any papers on temporal networks, but I also feel like it's a really new field.
Yeah.
What do you think of the notation used? Do you think it was like a good way to describe the problem? Could you see any improvements? Because that kind of thing can be really helpful for developing a field, just because it makes it more accessible to other people.
You know, I actually found it not bad. I guess particularly like it does get a bit, I mean, it does get a bit confusing, but it's quite consistent in the sense that like you have the time step, the layer in the network. Sorry, yeah. I guess the confusing thing is layer. I feel like they should come up with a different name. And then R for like the relation type. Yeah, I don't know. I don't know how else they could have done this, but I found it okay to like understand what was happening at different points.
Okay, nice.
Yeah.
They can't actually come up with new names because in the multi-graph, it's already called a layer. In a neural network, it's called a layer. So they can't change it, right?
Yeah. Yeah, it's true. But they are very good at saying like relation type R, the else layer of the GNN, et cetera, et cetera. I actually don't know. I don't know if anyone found like knows this, but what is this? Like I marked it because I have no idea where that's coming from or what that is, but I haven't seen tau like anywhere
Tau
else.
is, I think, their time step. So it's the I think. Let me look at the paper.
Yeah, I think it was something else. I looked. Oh no, yeah.
They have the tau here, but I don't know if that's like the same thing though, because what does it mean to concatenate the node embedding for node V, node U?
Yeah,
Then
it's
this is
using
like,
tau as a time step. If you
What
look in the
is-
preliminaries.
right. Oh, so they literally just concatenate the time step. That's interesting. So it's just like a number that represents the time step.
Yeah, I guess so. That could be an extension. Use a more sophisticated positional encoding.
Yeah. Yeah. No, I think you're right. Yeah, I don't know. So they mentioned because Peter, you mentioned scalability. They do say that they trained. Why did they say this? Hold on. Oh, yeah, so they used the GraphGym library, which I personally haven't played with before, and then they use an NVIDIA V100 GPU. Has anyone played with GraphGym? I actually never even heard of it before reading this paper.
Well, it may be very useful. It says it's a platform for designing and evaluating GNNs as originally proposed by a paper. We now officially support GraphGym as part of PyG. PyG is the Python geometry, which is what we use. Many others also use that. So maybe we should look into this.
So it's a library for evaluating GNNs.
Mm-hmm.
Interesting.
Designing and evaluating GNNs.
Oh, from Stanford. Cool.
Well, it's from Python geometric, I think. As well.
Oh, the PyG.
Or at least, actually, no, it's not from Stanford. It's one of Stanford's. There's a lab called Snap, I think, in Stanford. That's one of the main contributors.
Right.
But yeah, PyG.
PyG. Wait, PyG is PyTorch geometric.
Mm-hmm.
Cool.
If no more questions, should we end here?
Yeah, sounds good.
Thanks, Gerard.
Thanks,
Very interesting
everyone.
paper.
Thank you very much. Very interesting.
Cheers. Have a good day, everyone.
Thank you, Gerard. Cheers.
You too, thank you.
Thank you. Thanks.